let us get started with this module. We are going to deal with the multi-layer perceptron. Okay, we have sort of qualitatively studied the pros and cons of the different modes in which the learning algorithm can be explored. But now let us get into the details, the mathematical details of the multi-layer perceptron towards the derivation of the so called backpropagation algorithm. It was initially conceived by Paul Verbos and it has found significant applications to modern deep learning techniques, and I think this is the backbone of a neural network architecture based on the feed forward criterion. Now let us see how we can formulate this, right. We saw the formulation of the error setup, right. You got a sort of gist how to set up the error criterion. Now we will go deeper into the details. Okay. Let us consider a single layer of hidden neurons. So when I discussed earlier, I said we can have the input layer, we can have several layers of neurons that are termed the hidden layers, and then we have an output layer, right. But for the purposes of derivation, we will consider the single layer of hidden neurons, so that it is easy for you to understand how this works. From here we can generalize how it can work for different layers. Okay. Now let us discuss the architecture and then define all the variables and then derive the algorithm. Okay. Now at the input here we have these neurons, there is also the circle here. So the inputs there are I mean the neuron is really not a neuron here, because we do not have the functionality of a neuron. We just indicate these by these circles, but they are just inputs, right. Excluding the bias, we have m naught set of inputs. So this is excluding the bias, m naught inputs excluding the bias. So we saw the basic model of a neuron, because we have all these inputs and then we take W transpose X, we have this phi of W transpose X plus bias. So if I give you some input vectors, then you project it with the weights, then add the bias and take this nonlinear function. So this is what is basically happening here, right. I have all these inputs. Now these inputs are all connected to these neurons. So I have a single layer of hidden neurons, and let us assume that in the hidden layer I have m suffix 1 number of neurons. Again our convention is very important here, which I will indicate through red. 0 is the 0th layer, 1 is the first layer, 2 is the second layer, and the second layer happens to be the output layer, and 1 happens to be our hidden layer, and 0 happens to be our input layer. Okay. Now I also have these weights, these weights which connect the inputs to the nodes of the network in the hidden layer, and then from the hidden layer we have these synaptic weights which connect to the output layer, and this is still fully connected network. That is, there is connection from every processing element to every other processing element. And we introduce this bias because we have to bring in this function, right. You just have to recall this phi of W transpose X plus B. So in order to bring this bias, we have to introduce this in the input layer as well as in the hidden layer, and we will call this y0 of 0 and here it is y 0 of 1. Again this 1 within this brace indicates layer. This is very important in terms of convention, and 0 is just the coordinate, right, y 0 in this case, this is just the coordinate. Okay. Now we have these biases that are also connected to the processing elements, and this continues like this. Now let us delve into the details of the algorithm. You may wonder, here at the outputs we do not have any bias, we do not need any bias because it just gives us the functional signals. So therefore there are m suffix 2 number of neurons here, but in the hidden layer we have m suffix 1 number of neurons without the bias. So therefore it is m suffix 1 plus 1 number of nodes, and here we have m suffix 0 number of inputs without the bias. So this is a small detail. Now we have to formulate the equations. So let us do this in a systematic way. Okay. It looks very messy when you see this slide, but I think I have written down all the variables and it will be easier for us to single step through this messy or good looking slide. If you like equations, you see this good. If you are averse to it, maybe you find it messy, but in terms of conceptual understanding it is not so difficult. We can see through this very easily and quickly. Okay. Now we have these inputs in the hidden layer, they are basically the function signals, y 0 of 1 which is plus 1. So again, to note, our superscripts over all the variables, they indicate the layer number. So this is layer number, just to recall, and the subscript is basically coordinate number. Okay. Now we have all these functional signals, and these functional signals are connected through these synaptic weights, and let us imagine that we have a neuron in the output layer, right. This is neuron J in the output layer. So this is the jth neuron in the output layer, which is layer 2, and we are computing W transpose y here, right. So if you want, you can put an n for these signals also, indicating it is a time n, but for a bias it does not change with time. So therefore it is fixed to be plus 1, it is hardwired to be plus 1. Now this is the jth neuron. I will shade this in red if you want to make this clear. So this is our jth neuron. This jth neuron is connected to the 0th node in the hidden layer by the weight wj0. This is our indication. Similarly, jth neuron connecting with the ith functional signal is given by wj comma I, and again to recall, on the superscript it is a layer number, and in the braces it is the time instant, and j comma I here indicates the connection. Jth neuron in the output is connected to the ith neuron in the previous layer. Similarly, jth neuron in the output layer, which is in layer 2, is connected to m suffix 1 neuron in the hidden layer given by wj comma m1. Now we formulate the signal Vj of n, which is basically the summation of your y 0 times the corresponding synaptic weight. You take y0 of 1 multiplied by wj comma 0 of 1 and then take y1 of 1 with wj1 dot 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 so on till ym1 multiply with wjm1 and you sum this over. That is what we have in this equation. It is a linear summation. Okay. Now this wj is the local receptive field. This goes through a nonlinear function which is phi, and we get y suffix j of n corresponding to the layer number 2. That is the functional signal that we have, and this functional signal is our response through the network, right. So, I will indicate this in a different color, green here. So, this is our functional signal through the network. But again the careful reader, the careful listener or the student will realize that this is just a single hidden layer. So, if you were to generalize, you can think about cascading all these functional signals through the various layers, but for the purposes of illustration and ease of understanding, we are sticking to one layer, one hidden layer. Okay. Now, once we compute the functional signal, so I am just focusing on node j, right, indicated by y suffix j. We have the corresponding desired signal for this neuron given by d suffix j, and n indicates our time instant. This is just the detail throughout, okay, and we get the instantaneous error signal which is e suffix j of n, right. This sort of gives us the complete picture how we can compute the variables or some of the latent variables given the parameters of the network. Now, the functional signal at neuron j in the second layer, which is the output layer, at iteration n of course is given by this quantity. Just I am rewriting this in mathematical terms. So, yj in the layer 2 at time instant n is phi of vj of n in layer 2, right, and this we also call the local receptive field. Now, once we compute the functional signals, we can compute the error, because we saw in the previous slides that the error is basically the functional signal minus desired or desired minus functional, whichever way you want to think, because we take the square of the error anyway, right, and we do not care about the sign. So, you know what the desired signal is for neuron j in the output layer. You have computed analytically what the function signal is for this node. So, therefore, you can compute the error. You have that parameter available within your hand. What we have to do is apply a correction to the weight that is connecting neuron j in the output layer to neuron I in the previous layer at time instant n proportional to the derivative of the gradient of the error. That is the key idea. And what is this feel for this gradient descent, right. So, I have a performance curve. So, this is my performance curve. So, I will talk about these gradient descent techniques I would have talked about these gradient descent techniques in the earlier slides, but if you recall what the gradient descent does, if you have an error gradient pointing, let us say in this direction, which is given by the bold red, this is the error gradient, then we have to go in the opposite direction of the error gradient so as to reach the bottom of this bowl that we intend to go, right, because instantaneously we do not know how the error gradient is. It can be, if it is going in a certain direction, we have to go in the opposite direction because we do not want to go in the direction of the error gradient, right. We have to, this is how the error gradient is going. As you go away from the bottom of the bowl, you are making more and more errors. If you are coming towards the bottom of the bowl, then your direction is right. So, the error gradient is opposite to where the saddle point is. So, therefore, you have to apply a correction term that is proportional to the derivative of the instantaneous error with respect to the synaptic weights at time instant n, right, and there is a negative sign missing, but I will talk about these details when we go further down through the algorithm. So, this picture should be very clear. Now, this is the idea, right. The idea is sort of clear, that is we have to go down the gradient descent. Now, how do we decompose this error? Recall that the error is summation over all the instantaneous error energies over all the neurons, right. Now, when we take the derivative of the error with respect to the synaptic weights, we will have to do the chain rule, and this is what we get when we do the chain rule, sort of pretty straightforward calculus. So, I need the partial derivative of the error energy at time instant n with respect to the synaptic weight w j I at time instant n in layer 1. So, this is our sort of notation, right. All the synaptic weights are connecting from 0th layer to the first layer indicated by w j I of 0, and from the hidden layer to the output layer it is w j I of 1. So, this is sort of straightforward from our sketch of the architecture, right, and how we defined our variables. So, what we do is we do chain rule now. So, it is d error with respect to the, this is the sum error, which is the total error over all the neurons, and you take the partial derivative of this total error, I would say instantaneous error, with respect to the instantaneous error with respect to neuron j. This is instantaneous error with respect to neuron j, right, and then we take the partial derivative of the instantaneous error of this neuron j with respect to the functional signal in the output layer for this neuron j. So, throughout it is the same neuron j here except the last term. Then we take the partial derivative of this function signal in the output layer at node j with respect to the local reception field v suffix j. So, this is the local reception field, and this is the function signal, just to recall. So, you take the derivative of the function signal with respect to the local reception field and then the local reception field with respect to the synaptic weight. connecting neuron J in the second layer to neuron I in the first layer or the hidden layer. So, this is hidden, this is output. I think this becomes pretty clear, right. So, you see there are 4 partial derivatives that we need to compute as a consequence of this chain rule, right. So, again I recall, this is the total instantaneous energy and this is the synaptic weight. We need to take the partial derivative of the total instantaneous energy with respect to the synaptic weight Wji of 1, that is J is the neuron in the output layer and I is the neuron in the hidden layer. With respect to that, we need to compute the partial derivative, and that can be broken down into these 4 pieces. The total instantaneous energy with respect to the instantaneous energy with respect to neuron J, the instantaneous energy at neuron J with respect to the functional signal at neuron J, the derivative of the functional signal at neuron J with respect to the local reception field at neuron J. All these are within the output layer, that is at layer 2, and then last the local reception field at neuron J in the output layer with respect to the synaptic weight connecting the jth neuron in the output layer with respect to the ith neuron in the hidden layer. This is where the superscript changes its value and we have a 1 here indicating the connection. So, this is a detail. Now, I think once we get this concept here correct, we can proceed towards straightforward calculation of all the partial derivatives. Okay. Now, we take the partial derivative of the total instantaneous error over all the neurons in the output layer with respect to the instantaneous error in the jth neuron in the output layer, and that is basically Ej of n, because if you take summation half Ej square of n over all j belonging to the set of output neurons, you take the partial derivative, you are left with Ejn, right. This is straightforward. So, I will just erase this back. So, you can go back to your previous slides to get these variables, right. Okay. So, this is done, this is straightforward. Now, derivative of Ej of n with respect to the functional signal, that is the second term, right. This is term 1, this is term 2, this is term 3 and this is term 4. So, first term is straightforward, second 2 is pretty easy because the instantaneous error at the jth neuron is basically desired minus Yj, that is the convention we followed, right, and we take the derivative, we get a minus sign, minus 1 here, right. This is term 2, and then we take the functional signal and take the derivative, partial derivative with respect to the local reception field. This is where we have to be careful because what is this Yj? So, Yj is basically phi of Vj. I just put an n here to be consistent. I also put the indication indicating which layer. So, this is the basic equation. Now, we take the derivative is basically derivative of this nonlinear function, which is basically phi dash of Bj of n. So, this is also clear, this is term 3. Last term is now this Vj with respect to Wji, and we saw this equation that I wrote earlier, which is this equation Vj of n is basically summation I equals 0 to m1 Wji of n yi of n, and Vj is in the second layer and this Wji and yi are in the previous layer indicating it is 1, that is layer 1. Now, from this we get straightforward this equation here, right. So, this is yi of n taking the partial derivative. So, I will just write this here, Vj of n is summation Wji of n yi of n. Just to recall, this is what we have, and indicative of the layer numbers, right. So, this is also clear. We have all the 4 terms that we have. First term evaluates to be Ej of n in layer 2, second term happens to be -1, third term happens to be the derivative of the activation function evaluated at Vjn of 2, that is the local reception field at neuron j in the second layer, and the last term is basically the function signal at node I in the hidden layer. This is important. So, you do not have to remember or rote learn these derivatives as long as you get the picture how to compute all the variables within the network, some of the latent variables within the network, and then applying this chain rule. Okay. So, now we get our partial derivative of the total instantaneous energy with respect to the synaptic weight Wji within the hidden layer, and that evaluates to be this quantity, right. This is straightforward. Just multiply all the terms within the chain rule and you get this quantity here. Now, delta Wji should be proportional to the error gradient with respect to the synaptic weight, and therefore, if we introduce a learning rate eta which we can assume to be constant throughout the algorithm, then this is going to be minus eta times the derivative of the instantaneous energy with respect to the synaptic weight connecting the jth neuron to the ith neuron in the hidden layer. Okay, now this is important, right. To get this quantity, to get this derivative, we have to do all these calculations that involved 4 different partial derivatives. Let us define the local gradient as follows: delta j of n in layer 2 is given by minus the partial derivative of the total instantaneous error energy with respect to the local receptive field at time n, right. This is at the node j, right. This is at node j, and in the superscript I always indicate the layer number, and that you have to bear in mind. And it is called a local gradient because in the output layer we can get a handle to the error, because we can compute the functional signal analytically, we have the corresponding desired response. So, therefore, we get our instantaneous error and we have a handle to that error there. But if you recall, in the very beginning of this module we discussed that the error signal has to be propagated all the way backwards from the output layer to the weights that are connecting the inputs to the first hidden layer, right. In order to compute the change in the synaptic weights, we have to look at the gradient of the errors or the local gradients in each of these layers. So, this is very important, that is the conceptual feel for the algorithm, and for which we have to introduce this local gradient which is a function of the neuron residing in a particular layer, right. This is an important thing. So, getting back to the equations here. Now, delta j in the output layer is defined as Ej of n error times the derivative of the nonlinear activation function which is acting on the local reception field in the second layer. So, delta Jn is Ejn times phi dash of Vjn, and I keep the layer numbering consistent here. So, the adjustment to the weight delta Wji is given by this quantity which is eta times delta j n times yi of n. So, this is consistent with what we have. If you are confused with the local gradient, as long as you can recall the gradient descent rule and then how to take the partial derivatives, that is enough, because from there you can proceed forward. But it is helpful to define this local gradient as an interim variable, because using this you can update the weights pretty easily. So, therefore, I have given you this definition. Now, we shall proceed further. There are two cases. As I mentioned earlier, neurons can be in the output node as well as in the hidden layers. So, since we are discussing throughout with a single layer of hidden neurons, so we can have only two cases: neuron J is an output node, neuron J is a hidden node. When neuron J is located in the output layer, it is supplied with a desired response. This is very important because the architecture endows it with the desired response. We can compute the instantaneous error Ej of n associated with this neuron, and as a consequence computing delta Jn for that layer is very easy, right. For the output layer, computing the local gradient at the neuron J is very easy, because you use this formula that I discussed earlier. You get this because you have the handle to the error, you know the activation function, and the activation function we assume it is constant for all the, it is the same, not constant, it is the same for all the neurons. That is, we do not have a neuron which has one particular activation function and another neuron having another type of activation function. I mean, that makes the dynamics pretty complicated and difficult to tackle. Therefore, we assume the same activation function for all the neurons, but biological neurons could be different, we do not know. Now, coming back to this local gradient, it is pretty easy to compute because we know the activation function, we know the local reception field, we can compute the derivative of the activation function with respect to the local reception field at that node times the error which we have direct handle in the output node. But when we get to the hidden node, this is not straightforward because there is no specified desired response to that neuron. This is where there is another level of conceptual clarity that you need to have to understand the working of the algorithm, right. So, if you recall, from these output neurons you have these error signals that flow backwards from the output layer to the hidden layer, and you have to compute the sum of all the local gradients that are scaled by the synaptic weights connecting all the neurons in the output layer to a particular neuron in the hidden layer. This is quite opposite to how you had the computation done in the forward pass, where if you think about a neuron in the output layer, you are summing all the inputs or the functional signals from the hidden scaled by the weights. Quite opposite to that would be thinking about the error signals, where the local gradients of the errors are scaled by the synaptic weights and they are summed when you think about the neuron in the hidden layer, and this is very important. So, error signal for a hidden neuron must be determined recursively by working backwards in terms of the error signals of all the neurons to which that particular hidden neuron is directly connected to, right. This is very important, and again if you are sort of confused, just recall the layer numbers, see how the neurons are connected, and you will find this useful to derive it yourself. Okay, now with this conceptual clarity in mind, we proceed. Now, if J is the neuron in the hidden layer, then the local gradient delta J is minus the partial of the total error with respect to the function signal at that particular node in the hidden layer times the partial derivative of the functional signal with respect to the local reception field, and doing the straightforward math computing the terms in the partial derivatives, we get this equation. And just note the consistency of the negative sign throughout the process. Okay. Now we will follow our principle. Now we have to compute the partial derivative of the error with respect to the functional signal in the hidden layer. Now this is given by summation. Now we have the chain rule, right, because the error energy is basically half of Ek square for k belonging to the set of output neurons. So basically we take this derivative. So this is, we take the partial, so it is summation over all k belonging to the set of output neurons, Ek of n, where k belongs to the output neuron, Ek of n in layer 2 times the partial derivative of the error with respect to the functional signal at neuron j in the hidden layer. And you go further, now it is d by Ek by d by Yj. So you split this into two terms, d by Ek with respect to d by Ek upon d by Vk times d by Vk upon d by Yj. So this is again chain rule. But I think you have to be very savvy here about the layer numbers. So if you think about the diagram very carefully or the signal flow graph, it becomes very clear, right. So this is the error that you have at the kth node in layer 2 in the output layer, and this you are evaluating with respect to the partial at node j in layer 1, right. This is very important, this layer number is very important. So observe the layer number consistent with the error signal flow graph that actually goes backwards. Now if you have gotten this concept, it is straightforward. Now you just basically you have to compute the partial derivative of each of these output errors in the each of the errors in the output layer with respect to the functional signal. So therefore you have the summation over k, right. I will just put k belonging to C, it is sort of straightforward even without this belonging to C. Okay. Now we can compute Ek of n, so as straightforward, which is dkn minus ykn. So this is dkn in layer 2 minus phi of vkn in layer 2. Now with this computing the partial derivative of Ekn with respect to Vkn is straightforward. This is negative derivative of the activation function evaluated at node k, right. This is the local reception field. This is straightforward, but Vkn is this. Now if you take the partial of Vkn with respect to Yj, you land up with W Kj of n in layer 1, right. This is straightforward. So using these two equations you can plug this back. I would call this term 1. So these are, I will call this A, I will call this B, use equations A and B So, maybe I will call this term 2 here, possibly because this is term 1, which is straightforward that you can compute, and I will call this as term 2, and using A and B you can plug this in within term 2 and you can simplify your equation. So, now we have the big picture here. Now, folding all the partial derivatives together, the partial of the total instantaneous energy with respect to the local with respect to the function signal at node j in layer 1 is given by this quantity minus summation over k E k n times phi k dash V k of n times. So, these two terms are in layer 2. So, this times W k j, the synaptic weight in the between the hidden and the output layer, that is the kth output neuron is connected to the jth hidden neuron. Now, going by our definition, if we treat E k of n times phi k dash of V k n as the local gradient, then this is basically local gradient. This is the local gradient at node k in the output layer, and we link this with the synaptic weights between the hidden and the output. Now, with this we are sort of set, right. So, once we compute the partial derivatives and everything else, now the local gradient in the first layer, in the hidden layer, has to be computed. We have computed the local gradient in the output layer, right, and then we have to link that somehow. So, the local gradient in the hidden layer for the jth neuron is the activation function, derivative of the activation function evaluated at the local reception field, that is the jth neuron in the hidden layer, times this summation of the product of two terms that happen to be the synaptic weight connecting the output neuron k with the hidden neuron j times the local gradient of the output neuron at the output neuron k in layer 2, that is output layer means it is layer 2, right. This is given by this equation here, this is important. And observe the key difference conceptually, right. In the case of computing the local gradient in the output layer, that is for all the neurons in the output layer, it was pretty straightforward. We had the error and we could just compute the error times the gradient of the partial derivative of the error with respect to the functional signal, right. It was easy for us to compute, but in this case it is not, because as we go to the local gradient computation for a hidden neuron, then we will have to sum all the local gradients coming from the output nodes scaled by the synaptic weights, and that is the key idea, and that is reflected in this equation very carefully, and this is very important. And please pay attention to the layer numbers that are indicated in the superscripts, it is very important, otherwise it will be very messy if you have to code this up yourself. There are many packages available, and if you just plug into the packages you may not get a feel how the algorithm works. And the worst thing is, if you have to do research and come up with your own algorithms, unless you get a feel how the procedure works, you will not be able to develop intuition. So, therefore, pay particular attention to the layer numbers and all the superscripts and subscripts, though they look messy. If you pay attention to the signal flow graphs, you will find them very useful. Now, from this equation we can finally sketch the signal flow graph of an adjoint system pertaining to the backpropagation algorithm. So, we have all these errors E1 of n, E2 of n, so on till E m suffix 2 of n. right. So, this is in the output layer, we take the derivative of the activation function as a function of the local reception field V1 to Vm2. These are scaled by the local gradients delta 1 to delta m suffix 2, and then we scale them by the synaptic weights that are connecting the jth neuron in the hidden layer to all these scaled local gradients through the synaptic weights, right, and that is how we can compute the local gradient at neuron j in the hidden layer. I think with these tools in place, we can update the synaptic weights and then we can realize our learning update, right. Now, how is the updation done for the weights? The general rule is the weight correction is proportional to the local gradient times the input signal. The weight correction is proportional to the local gradient times the input signal to that particular neuron, right. So, if you just go through the math, so the proportionality is replaced by an equal to some constant term which is the learning rate times the local gradient delta Jn times yi of n. Again I have left it in a very broad way without indicating the layer numbers. If you are savvy, you will realize that there are two types of neurons, neurons in the hidden layer and neurons in the output layer. And why we have to make this distinction? Because the neuron in the hidden layer does not see the error directly, right, this is important. It does not see the error directly, and that is the reason why we want to bring in this distinction. Okay. Now, going by the derivation, for the output layer, that is neuron j in the output is connected to neuron I in the hidden layer. Now, delta wji of 1 at time instant n is eta times the local gradient at node j in the output layer times the input, which is basically the function signal yi of n, yi1 of n, that is the input, because this is the input from the ith hidden node to the jth neuron in the output layer. This is straightforward, and do the math in a straightforward manner, just similar to what you did for the output neuron. So, delta wji of 0, that is for the weights connecting the input to the hidden layer, this is given by eta times the local gradient at neuron j in the hidden layer times the function signal at node I. But if you recall, what is our yi 0 of n? This is basically xi, right, these are our inputs connecting. So, therefore, we can kind of straightforwardly do this computation, right. So, one small detail that you will have to think carefully, particularly when you are coding up the algorithm, the 0th coordinate y0 in the input layer and y0 in the hidden layer, this is always 1 because they are bias terms. So, do not let it floating and complicate the things. This is a DC bias, a fixed value plus 1, but it will be scaled by the synaptic weight, which would be a variable in the equation. Okay. So, this is a small detail, and I think we have derived the backpropagation algorithm, or at least we have given the details of all the steps that are required towards updation of the synaptic weights, which is basically how the learning should proceed, right. So, we will proceed further from this step towards summary of the algorithm. We will stop here.